Hi everyone, welcome to the topic on reporting data. In this topic we'll look at how to accurately report summary data. This includes measures of central tendency, measures of dispersion, shape of the distribution, as well as relationships and the empirical rule. Here are the learning objectives. We're going to look at how we calculate and interpret the mean, median and mode, how we calculate and interpret the range, variance, standard deviation and coefficient of variation. Lastly, we look at how we calculate and interpret the covariance and correlation. Measures of central tendency or central location relate to a summary measure of the centre of a data set. These measures include the mean, median and mode, with the mean being the most commonly reported measure. We often want to know, for example, what the average grade is in our class, what the average age of a group of people is, their average income and so on. The mean is measured by adding up all the values and dividing by the number of values. This is shown on the slide. X bar represents the sample mean. Sigma means the sum. X represents the values. So we sum the values and divide by n, which is the sample size. Lowercase n, that is. The formula for the population mean is similar. However, the symbol for the population mean is mu, which is a common for population values to be represented by Greek letters. Mu equals the sum of all the population values divided by uppercase N, which is the size of the population. As you can see, the mean is sensitive to outliers by the very nature of the calculation, where we are calculating and adding up all the values. For this reason, we often report the median when our data set has outliers. Here is an example of a mean calculation with the inclusion of an extreme value or outlier. As you can see, the mean is calculated as 154,286, but looking through the data, this does not typify the centre of the data. The median is not affected by outliers, as it is simply the middle of the data set. If the data set is an even number, then the two middle values are averaged to work out the median. Median is often used when reporting housing prices. Referring back to the salaries example, the median is the middle value, which in this case is 90,000. As a central value, this better represents the data than the mean of 154,286, as the median is not impacted by extreme values. The mode represents the most common value. A data set can have no mode, one mode, which we call unimodal, two modes, which is bimodal, or more, which we say is multimodal. Again, referring to the salary example, the mode is 40,000. The mode can be very useful when we're looking at inventory ordering. For example, if you're running a shoe shop, you're not really interested in the average shoe size, being the mean, or the middle shoe size, being the median, but what you're most interested in is the mode, which is the most common shoe size, so you can order more of those. The weighted mean is an important concept too. This is when some values have more importance than others, and thus attract a larger weighting. These weightings are used to calculate the mean. In this unit, different assessment components have different weights, so to work out the mean we need to apply these weights to the different values. Here is an example of calculating a weighted average. As you can see, a student has 3 assessments. The scores are out of 100 for each assessment. In this case, exam 1 and 2 are worth 25% of the final grade, and exam 3 is worth 50%. To calculate the student's average score, we could simply average the 3 grades of 60, 70 and 80 to get a mean of 72. However, this does not take into account the higher weighting given to exam 3. When applying the weightings, we multiply 60 by 0.25, 70 by 0.25 and 80 by 0.5, therefore getting a weighted average of 72.5. When reporting data, often the mean is reported and nothing else. This is unfortunate as a lot of information is missing. When reporting the mean, it is also important to report the standard deviation so that the reader gains an understanding of the spread or dispersion in the data. Getting a mean is one thing, but together with the large standard deviation, this tells the reader that the data is widely spread and perhaps the mean is not very useful. A small standard deviation, on the other hand, tells the reader that there is less variability or more agreement and consistency in the data. Let's now look at measures of dispersion. Range is a quick way to gain an idea of the spread of a data set. Each night when you watch the news on the TV, you'll be presented with the range in terms of the weather. we are often told the minimum and maximum temperature for that day, well, in Australia anyway. The range is calculated as the maximum value subtract the minimum value. It is clearly impacted by extreme scores, as these are the values used to calculate the range. It is a simplistic measure, but good as a quick measure of the spread of the data. I often use the range when checking my data to make sure the responses of my surveys are correct. That is, if I use a scale of 1 to 10 and there are no data errors, then I would expect each variable to have a range not more than 10. The variance is a more sophisticated measure of dispersion. It can be measured for the population or the sample. For the sample, it is represented by S squared, and it is calculated by subtracting each value from the mean, squaring these values so that positive and negative values do not cancel themselves out, then adding up all the values, then dividing by the sample size less 1. The standard deviation is then calculated as the square root of the variance. The standard deviation is therefore more user-friendly, as it is in the same units of the data, whereas the variance is in squared units due to the squaring of the data. For the population data, the symbol used is sigma squared for the variance and sigma for the standard deviation. As you can see, the formula is very similar in that each value is subtracted from mu, the population mean, squared so that positive and negative values are not cancelled out, and then added up. Lastly, the sum score is divided by the population size, which is capital N. Sigma, or the population standard deviation, is the square root of sigma squared, the population variance. Lastly, I can hear you asking yourself, why is the sample variance divided by the sample size n minus 1, whereas the population variance is simply divided by the population size n? Well, we can look at a bunch of simulations to demonstrate what I am about to say, or you can just trust me. The reason is that n take 1 gives us an unbiased estimate of the variance. You can think of it as a correction factor that produces a sample variance closest to the population variance. If we simply divide by n, we underestimate the population variance, and this is known as a biased estimate. Now, many students ask me how we determine a good or bad standard deviation. Well, there is no such thing. You need to decide for yourself whether the standard deviation or the spread in the data is acceptable. Given the standard deviation is in the units of the data, then there is no hard or fast rules that above or below a certain number is acceptable or unacceptable. One way we can bring this to a common language, however, is by computing a coefficient of variance, or COV. This is the standard deviation divided by the mean. We normally then multiply this value by 100 to get a percentage. Lastly, measures that describe the relationship between variables are the covariance and correlation. This will be discussed further when we look at regression. A correlation coefficient is a value that describes the strength and direction of the relationship between two variables. The sample correlation coefficient is represented by the letter R, and the population correlation coefficient is represented by the Greek letter rho, which looks like an italicized lowercase p. Note the correlation coefficients range from -1 to +1. The closer to +1 or -1, the stronger the relationship. The closer to 0 means there is little to no relationship. Here are some scatter plots showing different relationships and the corresponding correlation coefficients. In the top left, we have a perfect positive relationship, which means as one variable increases in value, so too does the other. The corresponding correlation coefficient is +1. This is interpreted as a perfect positive relationship. The sign positive shows that it is a direct relationship, and the 1 shows that it's a perfect relationship. I should note here that the variable on the vertical or y-axis is often the dependent variable, and that is what we are trying to predict. The horizontal or x-axis normally contains the independent variable or the predictor. The next scatter plot across, that is top line middle plot, shows an inverse negative relationship. The correlation coefficient is -1, showing that it is a perfect negative relationship. The next scatter plot, top line far right, shows a moderate to strong positive relationship. The correlation coefficient of +0.7 further demonstrates this. An example of this may be the amount of study hours and your grade. The more you study, the higher your grade, is the assumption. Okay, so unfortunately correlation coefficients only account for linear relationships, and in this case there is a slightly curvilinear relationship that perhaps better accounts for this relationship. Okay, now onto the scatter plots on the second line. First, there is a scatter plot showing a moderate negative relationship. As you can see, that with the data points spread out, we no longer have a perfect relationship, but we have maybe a more realistic and achievable relationship. An example of this might be number of hours spent shopping and money left in your bank account. The scatter plot in the middle, bottom line middle, shows no relationship. So as x increases, y does not change. It doesn't matter how tightly clustered the data points are to a flat line, it still indicates no relationship. Lastly, the scatter plot bottom right shows no relationship according to the correlation coefficient. But as you can see by the scatter plot, there is a clear and perfect curvilinear relationship. Example, it is actually a perfect negative parabola. This is a clear warning of the importance of always viewing your data in a plot, as correlation coefficients only account for linear relationships, and you can clearly miss a curvilinear relationship such as this one if we go straight to the correlation coefficients before looking at the scatter plots.